So welcome guys. Hope you're all fine. Okay. So in this video, we are going to solve different problems, of course, related to the modern control system. Okay. So we'll pick different questions and then we run through them together. Okay. So the main purpose of this video is just to help those preparing for a test from a modern control system. Okay, I'll help as much as I can. Okay, so here's the first problem is on the state-space representation. Okay, so the question reads, consider the system shown below. Okay, it's a third order system. You have the third derivative of y plus 4, the second derivative of y plus 5, the first derivative of y is equal to u, where u is the input and y is the output of the system. So we want to define the state. What represent this system in state space representation. Okay, just recall state representation derivative of equal to where the state of the system plus b u, okay, where u is the input, a and b are matrices, okay, and then y is equal to cx, where x again is the state, and then d u, where u is the input, y is simply the output, okay. Okay. Sorry for that. I'll just have to call them back after some time. Okay. So now we want to write our system in this form. Okay. We want to write our system in this form. So first of all, if you look at this is a third order system. So we need states to describe the system. We need 3 states. Okay. X1, X2, as well as X3. Okay. To describe the system completely. So we're going to say let X1 equal to Y. Okay. So X1 equal to Y is equal to Y. Okay. So now next, what are you going to do? You're going to say, okay, what if I differentiate this guy, right? Okay. What if I differentiate this guy here? So I'm going to say, oh, the derivative of x1. Okay. The derivative of x1 is equal to y dot, isn't it? Okay. So I'm just trying to differentiate both sides. And I'm going to call this guy as what? X2. So we can say therefore that x2 is equal to what? X1 dot. So x1 dot is equal to x2. Okay. And then similarly, we're going to say, oh, what if again I take the derivative of this guy, right? Okay. I take the derivative of what? Isn't it? Okay. Or I can differentiate again x1. Okay. X1 double prime. Okay. If I want, okay, this is y y double prime, and then this will be the derivative of what? X2, okay, isn't it? So we can differentiate x2, right? Okay. Let's differentiate x2. Okay. So x2 dot. Okay, say x1 double prime. Okay, let me just follow the procedure. Okay. X1 double prime. I'm going to do this guy again as a second derivative. Okay. This is it. I'm going to give you what? Y double prime as well. Okay. Y double prime. But y double prime, I'm trying to differentiate this whole equation, right? And this will give you what? X2 double prime. And I'm going to define this using another variable, right? So x2 double prime will be equal to x3, isn't it? Okay. This will be equal to x3. So we can therefore say that x2 double prime give rise to x3. Okay. Now next, someone is going to say, what if again I differentiate this guy 3 times? Let's go ahead and do that. So x1 dot to y dot, okay? This gives us what? X2 dot, and this gives us X3 dot, isn't it? Okay, X3 dot. But you are not going to say, oh, X3 dot is equal to X4, please. Remember that we want to describe our system using how many states? 3 states, okay? So you introducing a X4, it means you're introducing the fourth state. And this is a third order system, you can have 4 states to describe that system. So for us to find X3 dot, we need to go back and solve the equation for X3 dot, okay? So we say that for y triple, okay, or the third derivative of y is simply equal to x3 dot, right? So in place of the third derivative of y, you're going to put what? X3 dot, isn't it? Okay. So from that equation, remember that our equation is y dot plus 4y dot plus 5y dot. And I'm going to put just for by default, I'm just going to put 0y, right? Remember, the derivative is reduced, right? Okay, equal to u. So y double dot triple dot is simply equal to what? We say this is equal to what? Y triple dot is equal to what? From this information, it's simply x3 dot, isn't it? Okay, x3 dot. Oh, by the way, you actually trying to reduce this third order system to the first order differential equation. Okay, so you need to follow that, and then y double dot in terms of this is equal to x3, isn't it? Okay, so y double dot is simply equal to x3. So you have to make sure that your equation that you are getting, or your differential equation that arises from the state variable, is a first order differential equation where the highest derivative is simply 1. Okay, and then plus 5. What is y dot? Y dot is simply equal to x, isn't it? So y dot is simply equal to x 2. Okay, and then plus what is next? 0y. Okay, 0 times y, and the y is simply x1. I'm just going to write this by default as x1, and this is equal to u. I'm trying to solve for x3 dot. So x3 dot as our state variable, this is equal to, so I'm going to write this in the order of like x1, starting with x1, x2, and x3. So this will be 0x1 minus 5x2 minus 4x3, okay, and then plus u. So now let us write all the state equations that we have written so far. Okay, so x1 dot is equal to x2. Okay, these derivatives, let's write them, all of them together. And then x2 dot was equal to x3. Okay, and then x3 dot is equal to 0x1 minus 5x2 minus 4x3 plus u. Okay, so and then also don't forget to write the output equation. We say that y is equal to x1. Okay, so this is the output equation. Okay, so y it only depends on the what? X1 state variable. Okay, so now let us write this in matrix form: x1 dot x2 dot and x3 dot. Okay, this is equal to, okay, now we write this as a n by n matrix. Remember, this is an n by n matrix, matrix A, which contains the coefficients of what? X1, X2, and X3. Okay, so these are the variables X1, X2, and X3. Okay, and then plus B matrix, okay, and then times U. Okay, all right. So now these are a matrix. As you can see from x1 dot equation, you don't have x1, you don't have x3. So this position is for x1, this position is for x3. One, you have x2, the middle present x2, right? Okay. And then for x2 dot, you don't have x1, you don't have x3. So this is 0, this is 0. So what's the coefficient of x3 is simply 1, okay? And then x3 dot you don't have x1. X1 is simply 0. That's the coefficient of x1 there. And then x2 is -5. And then x is -4. Okay. And then, oh, of course, from x1 dot, you have u as well. There's no u, right? So yeah, can you continue filling in that? So u is equal to 0. Even x3 dot, there's no u there. U is equal to 0. What about x3 dot? X3 dot, the coefficient of u is simply what? 1. Okay. So that is it, your state equation. Now let's write the output equation. The output equation is simply 1 by n matrix, right? So just it's a row matrix, just as one row. Okay? So you can see that the output just depends on what? Y1, okay? So just based on x1. Okay, so again, you're going to write this as what? X1, X2, X3, okay? And then you see that x1 is just a coefficient, right? I mean, its coefficient just 1, right? And then meaning the rest are what? Zeros. X2 is 0, similar x3 is 0. So, and there's no d, okay? So d is equal to 0 here. D is equal to, so you can just write 0 times u. So this is a state space representation for our problem. Okay, now let us look for the second problem. I'm going to share the second problem of today. Which one is this? Okay. All right, so here it is. Let me just share it. Hope you guys are enjoying this presentation. If you don't, or maybe you have some suggestion, let me know in the comment section there. Okay, let me know in the comment section. Please comment and like. Don't be selfish, guys. Come on. Comment and like. Share. If something is good, like. If something is bad, criticize. Okay. Don't just be watching there like secretly. Huh? You just watch, guys, secretly. That's not good. Comment, like, subscribe. Okay. No, I don't make money from this. I'm just doing it out of passion, guys. Come on. I don't make money from this. They don't monetize YouTube in Zambia. I don't know. Maybe if they do. I don't know. But anyway, I'm just trying to, help, guys. So if you like something, yes, hit the subscribe button and also, yeah. Okay. So here's the next problem, guys. Okay. So the problem says, consider the system shown in the figure below with S, GP of S is equal to 1. And the system transfer function given by, okay. So we are told that, oh, the system transfer function is given by what? Which is f of s is equal to g of s. So this one is simply the open loop transfer function. Right? Okay, as you can see, this is the forward, right? It's the open loop transfer function, which is the product of gc and g of s, right? So we're given already. So what we need to do is to find the closed loop transfer function. Okay, so the question says determine the closed loop sensitivity with respect to parameter variations in K. Okay, so let us go ahead and do that. Okay, so we are given L of S, which is the product of GC of S, okay, and the G of S. Okay, and this is, we are told that, oh, this one is simply equal to K over S times S plus 5. Oh, this is K in the numerator, sorry. K over S times S plus 5, okay? Now, first of all, let's find the closed loop transfer function, by the way. So the closed loop transfer function, remember that generally simply the forward path gain or the open loop gain over 1 plus, okay? This is a negative feedback, so I'm going to put a plus, right? And it's a sensor. Sensor is a unit feedback, as you can see, it has a gain of 1, right? This will be 1 over G of S, right? So in this case, our G of S simply the forward gain is simply equal to what? L of S, right? So, anyway, I'm just confusing this two. There are two different G of S, okay? Don't confuse the two. So I can write this now as what? L of S, which is a forward gain, okay, or the open loop transfer function, divided by 1 plus L of S, right? Now let us substitute those values. So we have K divided by what? S plus 5, okay? And then in the numerator, so denominator, you have 1 plus K over s plus 5, okay? Now guys, here we're going to simplify this further. So by multiplying on top and down by what? The numerator of k, right? So the denominator of k is s plus 5. I'm going to do the same thing even here. I'll multiply by the denominator of what? K, right? Which is s plus 5, okay? So guys, now the next thing we're going to do is simply to simplify that. So T of S will be equal to, so if you multiply here, guys, the numerator and this guy and this guy will cancel out. So what you're going to end up with? You're going to end up with K divided by, even here again, remember that this thing is multiplied by this 4 guy, right? So S times S plus 5 times 1, you're going to have S times S plus 5. And if you multiply again, K over S times S plus 5, multiply by that, you just remain with a K, okay? Because these two are going to cancel out as well. So if you want, can you simplify this as what? K divided by S squared plus 5S plus K. Okay. All right. So now we have found the closed loop transfer function, isn't it? Now define the sensitivity. Remember that the sensitivity of the transfer function T with respect to change in parameter, say alpha. Okay. This is equal to what? The change in the transfer function. Remember, the change is simply the small change over the total value, isn't it? So they say the change is it's a change in the value divided by the total value, right? So now I'm writing this as partial of the transfer function over the total transfer function divided by, okay, the partial over alpha, right? Okay, like that. Let me just confirm. I think yes. So what does this become here? This becomes what? If you simplify this in here, this is 1 over t, and this guy becomes what? Is this the opposite I've done? Oh, come on, guys. Let me just check. Yes, I think sensitivity. Yeah. I think it should be the opposite. No, it's okay. The change in t over t divided by partial of alpha over alpha. Okay, let's see, guys. Let's see. Okay. So alpha is simply the variable that is changing, right? Okay. So this is equal to, remember you're dividing these two. So you can write this as what? Del t divided by e and then divide by what? Del alpha over alpha, right? So the rules of multiplication there, what can you do? Okay, so alpha goes on top, right? And then well, okay, let me just write like this. You have del e over e. This is times alpha over del what? Del alpha, right? So that this now can be written as what? Sensitivity of the cross function with respect to changing the alpha there. You get what? You're going to get, so this alpha can come on top of t, of alpha over t, and then times del t over del alpha. Okay. So yes, so now in this case, our alpha is k, right? So we're going to write this as what? Sensitivity with respect to changing the variable k, this will be k over t times del of over del of k, right? So we need to find these two, right? We have it already, k as the variable there. Let us first find what? Del t over del k, right? So t, we have it. So our t is simply equal to, remember this is a function of s, so I'm just not going to write t of s, guys. Okay, this is k over s squared plus 5s plus k, okay? So now let us differentiate this guy with respect to k. So del of t over del of k, okay? This is equal to what? So our variable here is k. So remember I have k in the denominator and also k in the numerator. You can use what we call quotient rule, right? So you're going to differentiate the two while holding the bottom function, right? Okay, just a reminder, if you have u over v, the derivative of this guy is with respect to whatever variable interface x is equal to what? U prime v minus v prime u, okay, divided by what? V squared, right? Don't forget this, okay? So you have, what's the derivative of k with respect to k? This is simply 1, u multiplied by s squared plus 5s plus k, and then minus, and then you differentiate the bottom function with the derivative of this thing with respect to k, again to be 1, because these guys are constants, so they're going to disappear, right? Okay. So this will be 1 times k in the numerator there, and then divide by s squared plus 5s plus k squared, right? So this now can be simplified as what? S squared plus 5s, okay, plus k minus k, okay, plus k minus k, right? And then divide by s squared plus 5s plus k squared, okay? Now, what is the next thing? Okay, the next thing I'm going to do is what? What's next, guys? We're just going to simplify, right? Nothing. So here you have s squared plus 5s divided by what? S squared plus 5s, okay? Sorry. And then plus k squared. Okay, so this is the change in t over the change in what? With respect to the change in k, right? Isn't it? All right. So now let us substitute this. And remember that this is the formula we're trying to use for sensitivity. K over t, right? We need to have this constant, k over t. So again, let us write k over t. How can I write k over t, guys? Me, I just want to simplify this. This same as what? K times 1 over t, right? Or meaning the inverse of t, isn't it? The inverse of t is simply by just flipping the denominator of t comes the numerator, and the numerator comes the denominator, isn't it? Remember this, right? So 1 over t just be flipping this, right? Okay, so this will be k times 1 over t is simply like flipping this guy, right? Yeah, getting a denominator goes there, numerator goes there, right? Okay. So you have, so you're going to have s squared plus 5s plus k, and then divided by k, right? So which k and k cancel out? So k over t just becomes what? S squared plus 5s plus k. Okay, so that's what you have, guys. Now next, let us find the sensitivity now. Okay, so sensitivity of t with respect to k, this just be k over t times del of t over del of k, right? So k over t is simply equal to what we found as what? S squared plus 5s plus k, and then multiply by, okay, multiply by del t over del k. Del t over del k is this guy there, which is s squared plus 5s divided by s squared plus 5s plus k squared, right? So this and one of that cancel out, right? This is a squared, so we're going to cancel out 1. But it just mean with what? S squared plus 5s over s squared plus 5s plus k. So this is our final answer. Okay, so guys, any questions, please? You're going to ask in the comment section if you are confused somewhere. Maybe something is not clear. Okay, let's move. So let's, the next question I'm going to share, guys, again, is here. Okay, just be patient. Next question is coming. Oh, yeah, there's definitions and define the state, the concept of state of the dynamic system. Please, I'm not doing with definitions here. Okay, all right. So here's the next question. Okay, just a minute. Oh, come on, why misbehaving? You need to behave properly. You are misbehaving. Okay. Okay, so we have this. Okay, here's the thing. Surprise. This is the question I'm going to share right now. You know it. Okay. So here's a question that is coming. Here it is. You had no idea, right? But yeah, here you have. Okay, so the question says, obtain the state space equations for the mechanical system shown below. Obtain the transfer function for the system from the state space equation. Okay, so this question has got a lot of steps, right? So, but anyway, let us see what we can do from this, okay? All right, so here, as you can see, you have a mass, you have a spring, and also you have what? The damper here, right? Okay. Yes, you have this a spring, this a mass, this a damper, then you have the force applied, U of T, okay? And then you have the displacement there, okay? Right, so we have to get the first, the what? The differential equation for this system, describing the motion of each of the elements in the system, right? Okay, so remember that the applied forces must be equal to the what? The opposing forces, right? So which forces, how many forces have been applied here? As you can see, there's just one force as the input force is applied there, right? And then the opposing forces, you have the force in the spring there, and the force in the damper there, okay, here, okay, due to friction there. So the force of the mass itself due to the acceleration, okay? So we have three opposing forces. So these the three opposing forces must be equal to the applied force. So let us write the equation there. Okay. So the opposing forces must be equal to the applied force, right? So how many opposing forces? So I'm going to start with the mass itself, right? So the mass is going to have a force due to its acceleration, right? As it is moving down, right? So you're going to have mass times the acceleration. Okay, that's the first force, right? According to Newton's what? Second law of motion, right? So mass times acceleration. What's acceleration? Is simply rate of change of what? Displacement, right? Isn't it? So this will be the second derivative of y. So this is the second derivative of y, okay? And then plus what? Another force here is what? Oh, from this damper guy, right? This one is based on the velocity of the system, how fast the system moves, right? So the damping constant there, okay, the viscosity constant there, and multiplied by what? Velocity of the system, right? Of this guy, how fast it's moving, right? So the velocity is simply what? The first derivative of what? Displacement, or the change, the rate of change of what? Displacement, and then plus the force again during spring. So this is equal to what? A times the displacement, right? Where K is the spring constant. And this is equal to what? The applied force, U. So these are function of time, but I'm not writing them as y of t, but you have to know, guys, these are just function of time, okay? So as you can see here, you have what? You have the second order differential equation, right? Which now can transform this guy to state space model, okay? So I'm going to take this guy now into state space model. Okay. So state space model, what do we do? So you're going to define your output. You're going to say, oh, y equal to what? So look, we have how many states here? Since the second order system, you're going to have how many states? States. Okay. You're going to have two states. Second order system, two states. Let's do it the way we did the first problem. Okay. So once you define this, you're going to also find the derivative of that, isn't it? So y prime will be equal to x1 prime. And since you differentiate this, you're going to find this. I mean, you're going to let this be the second state, right? As x2. So x1 prime will be equal to x2. So you can write this because remember we need to find the derivatives of these states, right? So we've already said that x1 prime is equal to x2. Okay. Again, let's differentiate this guy again, okay? So the second derivative of y double prime equal to x1 double prime. This is equal to, hey, what is this equal to as it? X2 prime, right? Isn't it? But come on, guys. You're not going to say x2 prime is equal to what? 3. Okay, you're not going to reach up to x3 because you just need space to describe this system, okay? So for us to find x2 prime, we're going to substitute here, okay? So let's substitute. So say the y double prime is simply equal to what? 2 prime, okay? Plus b, y prime is simply equal to what? 2. Remember, we're trying to do this guy to what? First order system, right? So once I have x2 prime there, I don't expect to have other primes here, okay? So this will be x2, okay? Plus k times what is y? Y is simply equal to x1. And this is equal to u. So let us now solve for x2 prime of m x2 prime equal to, let's write them in the order, okay, starting from x1, so this will be negative k x1 minus c b x2 plus u, okay. All right, now let us divide by m. x2 prime is equal to negative k over m x1 minus b over m x2 plus, this is the same as 1 over mu, isn't it? Okay. Right, so now as you can see, let me just write now this, the derivatives of these states. We say that x1 is simply equal to what? x2 dot. Oh, let me just write the other, the opposite one, right? x2 dot. So x1 dot was equal to what? x2 according to this here, right? And also x2 dot is equal to negative k over m x1 minus b over m x2 plus 1 over m u. Okay. All right, now let us see. So remember, we also have the output equation, right? Output equation is simply y is equal to x1. This guy just depends on the x1 state. Okay. All right, now let us write the state space presentation. So x1 dot x2 dot, just have two states. So your matrix A will be a 2 by 2 matrix, right? Okay. x1, x2 plus b, okay, matrix, and then times the u. Okay, so let us substitute this. I think I can write this guy better. Okay. Let us substitute here now. Okay, so x1 dot, you just have x2, isn't it? So meaning the position of x1 is 0, x2 is 1, right? Do you have u here? No, you don't have u, right? So in place of, you're going to put 0 here, the first row, this whole row, isn't it? And then x2 dot, in place of x1 of what? Negative k over m. So this negative over m. In place of x2, you have negative b over m, right? Okay. And then y, u, which is the input. You have 1 over m. Okay. So this is the state equation. And then the output equation, you notice that this guy, x1, row vector, this guy just have what? On the coefficient, right? The rest are zeros, right? Okay. So this is the state space representation. Now the second part says we have to find the transfer function of the system, right? The transfer function of the state space equation. So what do we do here? Remember that you have the state equation or the state space representation. You have x plus b times u, and then y is simply what? Cx plus b times u. Okay, let us find the transfer function of this. Remember that the transfer function is simply the ratio of the output divided by the input under the 0 initial conditions, right? Okay, so let us find the Laplace of this guy. So the Laplace of x dot is simply s, x of s, remember that's the first derivative, minus x0, right? From that's the Laplace of the first derivative. But we said that x0 is equal to what? 0, isn't it? Because that's the definition of a transfer function, right? Under 0 initial conditions. So we're going to remove this guy. Let's neglect this guy, okay? And this is equal to ax of s plus b u of s, okay? And then from this, let's solve for x of s. So I'm going to solve for x of s. So I'll take this s of x side minus ax of s equal to b u of s. Okay. All right. Next, what I'm going to do, the next thing is what? We're going to factorize it, x of s. So this will be s minus a times x of s. But guys, come on, a is a matrix, right? It's just a number, like a complex number. I can't subtract a complex number, a number from a matrix. Matrix subtract from it, impossible. For example, when I say 2 minus 1, 3, 1, 4 matrix, this is not possible, right? So what I'm going to do here, you have to make this to a matrix, right? You multiply by, now, you make sure that it doesn't change. It's the same matrix. It's the same number. So the number doesn't change if you multiply by 1, right? So that one in matrix called what? The identity matrix. Okay? S I minus A So I'm going to multiply S by the identity matrix. And that identity matrix will depend on what? Matrix A. So if it's 2 by 2 matrix, I should be a 2 by 2 matrix. If it's a 3 by 3 matrix, I should be what? 3 by 3 matrix. Okay. BU by S, right? And then from here, let us say X of S equal to, okay. This will be equal to what? This will be equal to Si minus A inverse. Why am I saying inverse? I'm dividing both sides by Si minus A, isn't it? So the division matrix, you can't just multiply matrix direct, matrix over matrix B, divide them now. You do the inverse, right? So the division matrix must inverse, okay? So it's more like we're taking the inverse of both sides. Okay? So this is Si minus A inverse times B times U over S, okay? All right, now the next thing we're going to do is to plug in this in the second equation. But before we do that, let's also find the Laplace of the second equation. Remember that our output equation is simply equal to Cx plus B times U. So this will be Y of S equal to Cx of S plus B U of S, okay? So Y of S, this is equal to C X of S, this is it. Remember S of X is Si. I'm substituting now here. Inverse B of S plus B U of S. So we can see that we can factorize U of S. Remember, U of S is simply the input. So of Y of S equal to C Si minus A inverse B plus B multiplied by U of S, right? And then divide both sides by U of S, you're going to have output over input equal to C Si minus A inverse times B plus B, okay? So this is what we call the transfer function of a state space model, right? This is a transfer function of state space model. Okay. Right. Now, what is the next thing? Okay, what's the next thing now? We need to find this, right? Si minus A and then inverse times B, blah, 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 blah. If you go back to our problem here, if you look at what we found here, we don't have D here, right? Our D is equal to 0, isn't it? Okay, so our D is equal to 0 there. Meaning that we can definitely disqualify D. We can just say, okay, D is equal to 0 even here. Let us write all the matrices that are there. A is equal to what? So A is simply equal to 1, 0, 1. Okay, you have A as 0, 1, negative K over M minus a B over M, I think. Yes. B over M. This is matrix A, right? And then matrix B is simply equal to what? 0, 1 over M. And then matrix C is simply equal to what? 1, 0, right? Okay. 1, 0. And then D is equal to 0. Okay. So now let us substitute them in this equation here. Okay. So let us substitute this. Okay. So first of all, let's find Si minus A. Remember that the order of operation in matrix is very, very important, right? You can multiply C times B first, right? Then you skip the number between there. Then that's wrong. So first, let's find Si minus A and then get the inverse of that. Okay. So Si minus A is simply equal to what? S with the identity matrix for 2 by 2, right? Remember, A is a 2 by 2 matrix. This will be 1, 0, 0, 1 minus A. Matrix A is simply 0, 1, negative K over M minus B over M, right? Okay, so this is equal to S here, 0 there, 0 there, S there, minus 0, 1, negative K over M minus B over M, right? Okay, so let us simplify this further. So Si minus A becomes what? So S, remember, when you subtract matrices, it's adjacent element minus adjacent, right? So S minus 0, that is S. 0 minus 1, that is negative 1. 0 minus negative K over M, that is positive K over M. And then S minus negative B over M, that is S plus B over M. Okay, this is Si minus A. Now let us find the inverse of this. So Si minus A inverse, Si minus A, its inverse will be what? Its inverse is simply just have to what? Find the adjoint of Si minus A, the adjoint matrix divided by the determinant of what? Si minus A. Okay. So how is the adjoint matrix? Adjoint matrix is matrix that you get just by, if it's a 2 by 2 matrix, right? It's very easy to find the adjoint. You just swap these elements, the major diagonal, and then multiply the elements in the minor diagonal by -1. Okay, it's adjoint matrix. So first of all, let's find determinant of what? Of Si minus A, right? So Si minus A determinant. Okay, this is equal to the product of the major diagonal there, S plus B over M, minus the product of the minor diagonal there, right? So the -1 by K over M, that is -K over M. So this is equal to S squared plus B over M, S plus K over M, right? Okay, that's a determinant, isn't it? Now let us find the adjoint. Adjoint of what? Si minus A. So just swap the elements, the major diagonal. So we have S plus B over M. And then this S will come here, right? And then multiply these guys by negative. This will be negative K over M, while this will be +1, okay? Now let us divide, right? So the adjoint of Si minus A will be equal to, for now, I can just write this as 1 over S squared plus, okay, B over M, S plus K over M, multiplied by the adjoint matrix. Same thing, right? Okay, so for now, I'm not going to divide those because this thing will become more complicated. B over M, this is 1, negative K over M, this is S there, right? Okay, now let us go back to our operation, right? So we have found this guy now, right? We have found that inverse, right? Now, next thing, I'm going to multiply by matrix B. Okay, so that inverse guy multiplied by matrix B. So I'm going to say I minus A, or this is actually, it's not adjoint, it's actually inverse, right? Inverse, right? Yes. So Si minus A inverse multiplied by what? B. So this guy multiplied by B. So I still have this 1 over S squared plus B over M by S plus K over M. Okay. S plus B over M. 1 here, negative K over M. This is S multiplied by matrix B. Matrix B is simply 0, 1 over M, right? So this is just a constant. You can even forget about it at the moment, right? Let not confuse you. Just focus on the matrices there. The multiplication here is row by column, remember? Okay, so this is a 2 by 2 matrix. This is a 2 by 1 matrix. So the order will be 2 by 1 as well, isn't it? Okay, to get just number of rows there in the first matrix, the number of columns in the second matrix, make it the order of the resultant matrix. No? So, okay. So row by column. So you're going to multiply S plus B M with 0. Okay, that is 0, and then plus 1 times 1 over M, that is 1 over M. So you have, this guy is still following us. Hey, let's not forget about him. S squared plus B over M, S plus K over M. Okay, and then this by this is 0 plus this by this 1 over M. So here you just get it 1 over M, isn't it? Okay, 1 over M as a result of multiplying this row and that column there. Now here negative K over M multiplied by that is 0, and then S multiplied by 1 over M. Okay, that is S over M, isn't it? Okay, and then now we are going to include C, right? So this guy multiplied by C, right? So this determinant thing, you can just keep it for now. Plus B over M, S plus K over M. Now include your matrix C. Remember matrix C is simply 0, 1 is 0, right? And then we still have this matrix 1 over m, and then S over m, right? Let's multiply now. This is it, row by column. So this is a 2 by 1 matrix or a 1 by 2 matrix. Okay, this is a 2 by 1 matrix. So the order will just be 1 by 1, right? Isn't it? That's 1 by 1 matrix. Okay, 1 no 1 column, right? So here just going to have this row multiplied by this column. So 1 times 1 over m, that's 1 over m plus 0 times this, S over m. So the answer just be 1 over m on top. Okay, 1 over m on top, and then divide by S squared plus b over m, S plus k over m. So that's the result, right? So you can multiply on top by m, right? Okay. So the transfer function, therefore, which is the ratio of the output to the input, becomes what? So I'm going to multiply by m on top, and then here by m, right? So m and m will cancel out, just mean with a 1. And then m by s squared, that is s squared, plus b over m times m, that is bs, right? K over m by m, that is k. So this now becomes a what? Transfer function. Okay. So this is the end of our function here. All right, let us move to the next problem. What's the next problem for today? I don't know. Let's see. Okay, right. So here's the next problem. So here's the next problem, right? Okay, guess what? Here. What's the next problem, guys? Okay. So the question reads, consider a system defined by the following transfer matrix. Okay. So the question says, determine the poles of the system and their multiplicity. Okay, so let's do that. Okay, let us do that. Okay, don't even have to worry about that. Let's do it together. Okay, let's do it together. Just a minute. I think I'm trying to check something. Yes. Oh, okay, great. Okay, where is this? What is this? I'm looking at. Oh, okay. Project presentation. Okay, fine. All right. All right. So let us see what we can do here. So we need to find the poles of the system and their multiplicity, right? So the poles is simply what? What are the poles of the system? The poles of the system is simply what? The characteristic equation of the determinant of your system, isn't it? Okay. So we need to find the determinant of this. And then the characteristic equation is simply the pose or the roots of the what? The denominator. Okay. So let us do that, okay? Let us do that. So first of all, I think I'm going to send this guy, okay, inside there, right? I'll send this guy inside there, okay? So 1 over blah, blah, blah there, I'll be sent inside there. So I'm going to distribute it. So G of S, okay, G of S simply equal to what? This is S minus 1. Oh, pushing myself properly here. S minus 1 divided by, okay, this is 1.25. So I will just divide everything by that, right? S plus 1, S plus 2. And then here you have what? S over, again, 1.25, S plus 1, S plus 2, right? And then here you have negative 6 divided by 1.25, S plus 1, S plus 2. And then you also have S minus 2 divided by 1.25, S plus 1, S plus 2. Okay, so this is the matrix that we have if I send everything inside there. Now let us get the determinant of this. Okay, so the determinant of G of S is simply equal to the product of the major diagonal element there. So to be S multiplied by that, which is S minus 2, S times 1, S minus 1, S minus 2. And if you notice, the denominators are the same, so it's more like you end up having a square, isn't it? Square number, right? So this guy becomes squared as 1.25. Everything else becomes squared there. And then S plus 1 squared, okay? S plus 2 squared, right? Minus, again, the product of that, that's negative 6S. So this makes it become positive 6S. And then divide by, again, the same denominator, right? Squared, S plus 1 squared, S plus 2 squared, right? Okay, next now, what do we do? The next thing is to do what? Combine these guys. As you can see, they have same common denominator, right? Let's not complicate things here. So this is S minus 1, S minus 2, plus 6S, 1.25 squared, S plus 1 squared, S plus 2 squared, right? So let us simplify. Let's expand that. That is 6 squared minus what? This will be 3S plus C. That's plus 6, 3S, right? I think you can check that. Plus 2 if you were to multiply here and simplify everything. You must be able to get that right. Over 1.25 squared S plus 1 squared, then S plus 2 squared, okay? Okay, now next thing we're going to do what? Let's factorize the top one. I think there's some poor zero cancellation there. Okay, let's factorize that. We have S plus 1 and S plus 2, I think, yes, as the factors. And then divide by 1.25 squared S plus 1 squared S plus 2, right? So you can see that again, this squared. These guys are poles that are cancelling as well as the zeros that are cancelling. So this 0 and there they're cancelling. And then this 0 here and the pole there, they're also cancelling, right? So we're going to have what? On top, we're just going to have a 1 divided by 1.25 squared. This just be S plus 1, S plus 2. And then poles are simply the roots of what? The denominator, right? Of the first pole as S1 at -1, right? If you solve, we equate this guy equal to 0. And then the second pole, S2, is equal to -2. And the multiplicity of this function is what? Equal to, again, say 1. There's no repetition, right? There's no repeated roots in short. So because repeated roots give you multiplication, right? Multiplicity, isn't it? Okay. I can just say multiplicity just equal to 1. Okay. Each one of them doesn't just fit once, right? Is equal to 1. Okay. Let's move. That's the end of this question. Okay, very short, isn't it? Yeah, it's very short. Okay, here's the next question, guys. Okay, here's the next question. Okay. Okay, here's the next question. Let's do about 2 or 3 more questions and then we end. Here's the next question, guys. Here's the next question. Here's the next question. Here you go. Okay. So the question reads, for the system given by blah, 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 that, where you are given the matrix A, B, The system uses the state feedback control U is equal to negative KX. Let us choose the desired closed loop pause at S1 equal to S1 2, which is negative 2 plus or minus J root 2. S3 is equal to whatever that, right? Determine the state feedback gain matrix K. That we need to choose to place those poles at that location. So this is just a problem on pole placement. Okay. So there are three methods that are used when dealing with what pole placement method. So there is what we call Ackermann's formula. There's what we call direct substitution method, and also there's what else? What's the other formula as well again? Okay. Yeah, the controllability formula, right? That involves controllability. Yes. So what do we do here? Which method are we going with? Oh, I don't even know which method I should do right now. Okay, I don't even know. But I like direct substitution though. It looks so simple and straightforward and easy to understand. Okay, but anyway, let me just do the observable canonical form method, I think. So the controllable method, I think. I don't know which one I should use. I'm just confused myself. I'm just feeling like I'm confused. Which method should I go with? I don't know. I don't know which method I should go with. You guys, are you going to suggest which method? I'm trying to look for the method that is going to be easy to explain. Oh, there is actually a video where I solved using the direct method, right? Direct substitution method. I solved a similar problem. So can I do something different today? Can't I do something different today? I do Ackermann's formula, I think. Okay. Let's see if I can use Ackermann's formula. Let me see if I can use Ackermann's formula. Just a minute. I hope I'm not delaying you guys. Am I? No, just have to chill a bit. I'll be back. I'm just trying to look for the formula that we need to use here. Okay, so the Ackermann's formula works like this, guys. I'm going to use Ackermann's formula here. So I'm going to apply Ackermann's formula. The other method I use direct methods, right? I've used this for many times. So I'm going to use Ackermann's formula. Ackermann's formula works like this, guys. Here is a formula. You find that K is gained by what? This is a 3 by 3 matrix, right? Okay, so we're going to have 0, 0, 1. Okay, so this is a row matrix. And then what's the next thing now? The next thing is to multiply by what? M inverse. And what is this M inverse? Yeah, okay, you need to know what this M inverse means, right? And then times phi A matrix. What is M inverse? Should we discuss it now? Should we discuss it now? Shall we? So what is M inverse? Okay, so the M inverse is a control bit matrix, right? Okay, simply a control bit matrix. Don't even know what about that. Okay, the inverse of the controllability matrix. Okay, so remember that for 3 by 3 matrix, your M is simply equal to what? For 3 by 3 matrix, M is simply equal to what? Okay, B, AB, and then B squared, right? Right. That's your M for 3 by 3 matrix. Okay. Okay. All right, so let's start. So first of all, to check for you when you do placement method, you have to check the system is what controllable. Okay, so let's find the controllability matrix. So M is equal to B, AB, and then AB squared, right? So our B is equal to that. Okay, so our A is equal to it's already in the controllable canonical form 0, 1, 0, 0, 0, 1, -2, -6, -7, and then B is equal to 0, 0, 2, okay. So let us find AB and AB squared, right? So AB will be equal to 0, 1, 0, 0, 0, 1, -2, -6, -7. Oh, so -7. I'm getting 27. And then multiplied by B, 0, 0, 2. So this is a 3 by 3 matrix. This is a 3 by 1 matrix, right? So the order, the resultant matrix is what 3 by 1 as well, right? Okay. Okay, so let us multiply. So row by column. So 0 times 1, okay, plus 1 times 0 plus 0 times 2. So you have a 0 here. 0 by 0, 0, 0 by 0, 0, plus 1 by 2. That is just a 2 here, right? And then finally, -2 by 0, 0, -6 by 0, 0, -7 by 2, that's -14. Okay, we move, right? That's -14. Now, what's next? We need to find AB squared, right? Oh, sorry, A squared B. I'm sorry, guys, here I made a mistake. This should be A squared B, not AB squared, okay? I'm so sorry. This should be A squared B. Oh, why did you remind me, Aaron? A squared B should be was what? A times AB, isn't it? Okay. Because A by A squared, right? So this is A by AB. Please don't waste time to find A squared, guys. Okay. Why should you waste time start finding A squared? Okay, and then times AB. So our AB will be found as 0 to -14, right? Again, you do the same thing row by column. So 0 by 0, that's 0, plus 1 by 2, that's 2. 0 by -14, that is 0. So the first element is into what? 2, right? And then 0 by 0, 0 plus 0 by 2, that's 0 plus 1 by -14, that is -14. Okay. And then finally, -2 by 0, that is 0. -6 by 2, that is negative. And then we also have the other value there, which is the, where's my calculator? I've just lost my calc. Oh, let me just get my calculator here. It's not even here. It's not even here. Where did I put it? Oh no, I've lost it. Oh, okay. I can't find it. Let me find my calculator here. I don't want to trouble my head at calculating all those things. Okay, -6, this is -12, plus 7 by 14, right? 7 by 14. So that is 86, isn't it? So this is A squared B, right? Okay, so that is our A squared B. Now let us write our matrix. Which matrix are we writing? The M matrix, right? Okay. The M matrix will be AB squared. Let's put them together. So our M matrix B, what is matrix B? Is 0, 0, 2, right? 0, 0, 2, and then AB, matrix AB is 0, 2, -14. And then A squared B, that's 2, -14, 86, right? Now let us find the inverse of this. So as you can see, this matrix is what? Completely state controllable, because let's find the determinant of this for it, I mean, whether it's controllable or not, right? So let us find the determinant of this guy. Okay, so for us to solve for the determinant of this guy, what are you going to do? Remember, it's plus, minus, plus. Don't forget this, okay? What are you going to have? The first element here is 0, so there will be no change. They're going to have 0 multiplied by the cofactors of this and find the determinant and all that. You notice that our determinant just be 2 multiplied by, cancel this just be this by that, right? So this will be 0 multiplied by negative 4, and then minus 2 by 2, right? So this is negative 4 there, right? So the determinant is simply equal to negative 8, and this is not equal to 0. So since the determinant is not equal to 0, what do you have? What do you say? The system is what? Completely state controllable, okay? All right. Now, let us find the M inverse. Remember the formula, Ackermann's formula need to have M inverse, right? Because those are the big things you need to know, right? So M inverse is equal to what? The adjoint of that matrix by determinant, right? So this can of the matrix A. Matrix M, sorry. What's the adjoint of matrix? So how do you find the adjoint matrix? You're going to find individual determinants for each element, right? So let me explain how you can find the inverse of a 3 by 3 matrix, okay? In case someone has forgotten how to do it. Okay, so you're going to find the more factors for each, right? So this one here, the first, remember the first is plus, minus, plus. The second row should be what? Minus, plus, minus, okay. And the third row should be what? Plus, minus, plus. As you can see how the signs are what? Are varying, isn't it? Okay. So that's, we are going to get the adjoint of that, right? Now, let us find dominant factors for each matrix, right? For each small matrix. What do I mean here is this. We're going to say, oh, for this one now, for me to find the element at this position, I'm going to say, okay, this element 0, I'm going to form a very big matrix, right? How should I? Okay, let me just say 0 multiplied by what? So when you cover this guy, what do you have? You have this multiplied by this, that's by 86. Okay. So 2 by 86. So I'm going to have, let me just write 2 negative 14. And then this negative 14 by 86, right? Isn't this what we have? Yes. By 86. Then multiply this guy by 0. And then you move next to the next element. Move to the next element there. Minus 0, right? Next element will be minus 0. Multiply by, so you cover that, you're going to have 0, 86 there, right? 0, negative 14 here. And then to here, you have 86 there, right? And then we're still in the first, right? And then the last one we positive 2, right? Multiply by the determinant that you get again by covering the rest, isn't it? That's the adjoint matrix I'm forming, right? So if you cover that, you remain with it. 0 here. Okay. You remain with what? A 2 there. And then remain with you again. A 2 here, negative 14. Okay. So that's the first row. Now let's move to the next second row. Second row now, we are going to do with this guy, right? So we have negative 0 there. Although it doesn't make sense writing negative, but we're just going to write what you guys can follow. Okay, and then you cover this row, you cover that column, which element remaining, you have 0, you have a 2, you have negative 14, you have 86, right? Okay, this is what you have. Similarly, you are going to do the same thing for negative for 2 here, right? Oh, what have I done? For 2 there, right? So you have positive 2. And then again, you form its cofactor, right? So cover this, you have 0, negative 14. Okay, 286 there, right? Okay. And then finally, you have this negative 14. Now, yes, it's negative 14, and this negative that you're going to include there has to be the 14, right? Okay. and then multiply by, so you cover that, you have 0, you have 2, you have 2, you have negative 14, right? Okay. And then now let us see, do the last one, the last row. Okay, the last row. The last row, you're going to have what? Okay. Positive 2 here as the first element there, right? Positive 2 there. And then now you start, you do what? Oh, sorry. This is the, this, let me check. It's the mistake that I made. Okay, I'm sure I made a mistake. When I had 0 here, I'd covered this and this, and at this matrix 0 to 14, 86 is good. Okay. And then when I had positive 2 here, what did I cover? I covered 0, have 0. Here is a mistake now. So it's 0 to 286. Okay, not 0 14. Yes. Yeah. Be careful here, right? Be careful there. Okay. And then we had 14 here. I have to cover this and have to cover that, right? So I need to have 0, 0 to negative 14, right? Yeah. So here you need to have 0 as well. Okay, better now, right? And then I'm doing with this row, the last row. Here, positive, right? So I'll cover this and I'll cover that. So I have 0 to negative 14. 0 to, and then to negative 14. Okay. All right. And then next, this is negative 14. Negative, going to positive, right? Positive 14. Okay. So this will be equal to what? So you cover that column and that row. You have 0, 0, right? 0, 0. And then to negative 14. And then finally you have 86 there, right? For 86, which column am I covering? You can cover that and that row, right? So 0, 0, 0, 2, right? 0, 0, 0, 2. So this is a big matrix. Is this a matrix into form, a 3 by 3 matrix, right? Let's just counter check, okay? Let's just counter check, guys. It's very important to counter check, right? Before you do anything. So when there's 0 there, when you cover this 0, what matrix do you form? 2, negative 14, negative 14, 86 is correct. When you cover this 0 here, what matrix do you have? 0, negative 14, 2, 86, correct? And anywhere the positive 2 there, when you cover this, what matrix do you have? 0, 2, 2, negative 14, okay? And then you add 0 here, you cover this column and the row where that 0 belongs. You have 0 to negative 14, 86, okay. And then when you add 2 here, this 2 in the middle, so cover the column and this row, 0 to 286, okay. And then when you add 14 there, you cover its column and this row, 0, 0 to negative 14, okay. And then you add it here, right? That's positive 2, isn't it? You cover its column and its row, 0 to negative 14. And then when you had 14 there, here, for this and that, 0, 0 here, 2, negative 14, okay? And then the rest is what we just remove, okay? Okay, so all is well. And then remember that you have to divide by what? The determinant, right? So I'm going to say this now, this over what? Determinant negative 8, okay? For now, divide by negative 1 over 8, right? So let us find the individual determinant for each, right? So this you have 0, so it means everything will be 0, right? Now, so 1 over negative 8, right? So don't have to bother there. That will just be 0. Even this guy also be 0 there, right? What about this one here? You're going to have 0 minus times negative 14, that is 0. And then minus 2 by 2, that is negative 4. Negative 4 by 2, that is negative 8, isn't it? So negative 8 here, right? And then in this position again, you're going to avoid 0, right? And then this will be 0 by 86, that is 0. 2 by 2 is 4, minus 4. Minus 4 by 2, that is minus 8, right? Okay, and then and here you're going to avoid 0 because this is 0, this is 0, so over will be 0 there, right? Okay, and then you are here 0 by negative 14, that is 0, and then this will be 2 by 2, that is negative 4, and then by 2, that is negative 8. Okay, and then here again you have a 0, right? Even here again you have what? A 0. Okay, so let us divide by negative 8 because now we're dividing by determinant. So every element divided by negative 8, what do you have? You have 0 here, you have 0 here, you have 1 there, you have 0 here, you have 1 here, you have 0 here, you have 1 here, you have 0 here, you have 0 here. You divide by negative 8. So this is the inverse of what? Our control bit matrix. Okay, that's our inverse. Okay, it's more like an identity matrix swapped, like exchange, right? Isn't it? I don't know how we can say it. Does it have a special name? I don't know myself. Okay, so that is M inverse, right? What else are we supposed to get? We're supposed to get phi A. Phi A matrix simply got what? 3 plus, I can say alpha 1 squared, right? Plus alpha 2, right? Plus alpha 3 times I. So what are these alpha? These alpha are the coefficients of the what? The given characteristic equation. So let us form the characteristic equation from the given poles, right? So we are given the poles that are desired, right? The desired poles should be placed at what? You have S1, 2, so this is a complex. Yeah, this is negative 2, plus or minus J, the square root of 2, right? And then S3 is equal to negative 10, right? So you have this one. So you're going to write this equation. S mu1, S mu2, and then S mu3, right? So let us put where mu1, mu2, and mu3 are simply the points that you have, and then expand, and then get the characteristic equation from there. So S minus mu1 will be negative 2 plus J root, right? So this will be plus 2 minus J root, right? Doesn't matter which one is mu1. And then S plus 2 plus J root, right? Okay. And then what is the next thing? The next thing is simply to do what? Multiply by S plus 3, right? Sorry, plus 10, isn't it? We have to expand this. The expansion of this, remember that guys, this thing came from where? This thing came from where? Okay, it came from like complete the square, right? So you had something like this, S minus 2 squared, right? S minus 2 squared, and then plus what? This guy is squared again, it just be what? Just be 2, isn't it? Okay. So this is where it came from. Okay. S minus C. Okay. No wonder of that minus. Sorry, S plus 2, not the minus. Okay. Because of those are the poles, right? That's S plus 2. So S plus 2, this number, just square it. Okay. Not worry about it, just square it. So that's S plus 2 squared, and then S plus 10. So that you can expand it so quickly. Okay, so this is the characteristic equation, right? Okay. Now it's equal to what? So let us expand that. You have S squared first plus, that is a 4S plus what? 6, isn't it? Right? And then S plus 10, right? When you expand, this is S squared plus 4S plus 6, isn't it? Okay. And then let us distribute again. This is S cubed plus what? This is a 10S squared plus that's 14S squared, right? Okay. plus, I don't know if it's 40s, and then plus 60, right? I think that's how it is, isn't it? You can check there, I think. I don't know if I made a mistake or somewhere. Oh, that should be 46 because this 6 will be A6S as well. This should be 46, right? That's 46S. And then plus 60, yeah. All right. Now these values here, the coefficient of, so our alpha 1 is simply the coefficient of S squared. Okay, our alpha 2 is the coefficient of what? S. And then our alpha 3 is simply a constant, right? Okay. So our alpha 1 will be equal to 14. Our alpha 2 is equal to what? 46. Our alpha 3 is simply equal to 60. So these are the values you need to put here. Then multiply by matrix A. So those you see the alphas are the values you need to put there, right? So we're going to say phi A, matrix phi A will be equal to matrix A to the power 3 plus alpha 1 is 14 A squared, right? Plus alpha 2 is 46 A, alpha 3 is 60 times identity matrix, okay? For 3 by 3 matrix. Okay. So first of all, let's find A cube. So A cube is simply equal to A by A squared, right? So let's get A squared first. So A squared is simply equal to what? Our matrix A multiplied by twice itself, right? Multiplied by itself, right? Okay, so 0, 1, 0. Okay, 0, 0, 1, -2, -6, -7. This is our matrix A, right? And then again multiplied by matrix A itself. 0, 1, 0, 0, 0, 1, -2, -6, -7, right? So let us multiply this is a 3 by 3 matrix. So the order again will be 3 by 3 matrix, right? So 0 by 0, that is 0, okay? Row by column, right? So 0 by 0, 0, plus 1 by 0, that is 0, 0 by 2, that is 0, right? So the first element here should be equal to 0. Okay, again, the same row, 0 by 1, that's 0, plus 1 by 0, that is 0, plus 0 by 6, 0. So I have a 0 here as well. And then the same row, 0 by 1, 0, that is 0, -1 by 1, that is -1, okay? And then 0 by -7, that is 0. If you add all of them, you get -1 just, right? Okay. Second row now, 0 by 0 is 0, right? 0 by 1 by 0 again, that is 0. 1 by -2, that is -2. So here you're just going to end up having -2. And then again, 0 by 1, that is 0. 0 by 0, that is 0. 1 by -6, that is -6, okay? Again, the same row, 0 by 0, 0, okay? 0 by 1, that is 0. 1 by -7, that is -7, okay? Cool. Let me just check, let me see. Oh, where did I get this -1 first? When I multiply the third. 0 by, that's +1 or -1. Let's be +1, okay? This number is +1 or -1. Where did I put -1? Come on, guys. Okay, that's +1, right? And then -2 by 0, that is 0. And then -6 by 0, that is 0. Okay, -7 by -2, that is 14, right? And then -2 by 1, that is -2 plus, okay? Remember you're adding, right? -2 by -6 by 0 is 0. And then plus -7 by -6. What is 7 by 6? That is 42. So the first one we have the -2 plus that is 40, I think. If I'm not mistaken. Let me check. -2 by 1, that is -2, plus -6 by 0, that is 0, plus -7 by -6, that is 42, plus -2, that is 40, I think. Okay. And then finally, you have what? Again, -2 by 0, that is 0, -6 by 1, that is -6, and then -7 by -7, that is what? 49, right? 49 minus 6 because of negative 6 here. That is what? 43, I think. Okay. That is 43. So that is a squared, right? Now, having found a squared, we need to find a cubed, right? So a cubed is simply a by a squared, right? There's a lot of work to do here. A by a squared, right? So let us multiply that guy by matrix a squared, okay? So a, the same matrix a, 0, 1, 0, 0, 0, 1, -2, -6, -7. Now multiply this guy by matrix a squared, right? 0, 0, 1, -2, -6, -7, 14, 40, 43. Let us multiply again. Row by column. Okay. The first row, 0 by 0, that's 0. 1 by -2, that is -2, right? So the first row here becomes going to have -2 there. Again, 0 by 0, that's 0. 1 by -6, that is -6 is going to come here. And then 0 by 1, that is 0. 1 by -7, that's -7 is going to come here, right? Okay. All right. And then the second row, 0 by 0, that is 0. 0 by -2, that is 0. 1 by 14, that is 14, right? And then 0 by 0, that is 0, 0, and then that is 40, right? 0 by 1, that is 0, okay? 0 by -7, that is 0. 1 by 43, that is 43, okay? So this is going to come here. And then -2 by 0, that is -2. -2 by -6 by -2, that is 12, right? 12 there. And then plus -7 by 14, right? Okay, -7 by 14. So you have -86 here. Okay, I don't know, you can check that out. And then -2 by 0 is -0. Oh, that is 0, sorry. And then -6 by -6, that is at 6, right? Then -7 by 40. So you're going to add them. -7 by 40. So it's have -244. How? I don't know. I'll check. Okay, I'll check why is that the case. Okay. -2 by 6, that is 12. Why did I get 6 here? 12 plus -7 by 40. Hope I haven't made any mistakes there. That's -268 there. Okay. All right, and then finally, -2 by -1, that's -2. Okay, -6 by -7, that is 42, right? And then -7 by 43. -7 by 43. I'm getting -261. Anyway, let's see. These numbers are getting so big. Let's see what we can do from here. What is it, right? So now let us write our equation and add everything, right? So we have equation, you have cubed, right? So start with a cubed. -2, -6, -7, 14. What is it? This is a 40. Yeah, it's a 40. And then 43. This is -86, -268. And where is -268 come from? Okay. And then -261. And then plus. Remember, we're saying multiplying 14 by squared. And what is squared? Squared is this matrix. So let's multiply this guy by 14, right? I'm going to do it direct. So 14 by 0, each element has multiplied by 14, right? We're going to have 0, 0, 14. This will be -28. And then 14 by -6 by -6. That is -84 here, right? And then 14 by -87, right? 14 by -87, that is 84 here, right? And then 14 by -87, 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 right? 14 times negative 7. That's negative 98, right? Okay. And then 14 by 14, right? So we're going to 14 by 14. That's 196. Here. And then 14 by 40. Okay. That's 560 here, I think. And then 14 by 43. That's 602. Okay, so that is it. 14 times a squared. And then in the next one is what? 46 by a. So 46 by matrix A, right? Matrix A by 46. So each element in matrix A multiplied by 46. The first one be 0. You're going to 46. This will be 0, 0, 0, 46. 46 by negative 2, that is negative 92, I think. Yeah. And then 46 by 6, right? By negative 6. That is negative 76 here, right? And then 46 by 7. That's negative 322. Plus, and then finally, you're going to have alpha 3 by I. So our identity matrix simply 0 in the major diagonal. So multiplied by 60, so we're going to have 60 in the major diagonal, right? Okay, now let us add each element, right? So this is the end result. This is 5A, right? Remember, we're getting 5 of A, right? So 5 of A, therefore, will be equal to, so let's add each adjacent element, right? So negative 2 plus 0 plus 0 plus 60, that is 58, right? Okay, negative 6 plus 0 plus 46 plus 0, that is 40, isn't it? Negative 7 plus 14 plus 0 plus 0, that is 7. 14 plus negative 28, that is negative 14, right? Negative 14 plus 0 plus 0, that is negative 14. 40 minus 84, that is negative 44. Negative 44 plus 0 here is negative 44. Negative 44 plus 60, right? That's 14, right? Okay. And then 43 minus 98 plus 46 plus 0, right? So 43 minus 98 plus 46. So I'm getting negative 9 here. Okay, let's see why I'm getting negative 9. And then next, you have negative 86 plus 196 plus negative 92 plus 0, right? That is what? In here. And then negative 268 plus 560 minus 276. So this is 16 here. And then finally, negative 261 plus 602. How did I get 602? I don't know if so, even not understand. I got to 602. And then minus, I don't know if it's 322. I don't know how I got it. If plus 60. Anyway, let's assume that I didn't make any mistake, right? Let's see how the answer is going to come out, okay? Okay, so that's why now let's remember that K is simply got what? 0, 0, 1 multiplied by M inverse, right? So M inverse we found is what? Found M inverse as what? 0. What was the M inverse? 0, 0, 1. Some ones are so right. 0, 0, 1, 0, 1, 0, and then 1, 0, 0 like this. And then multiplied by 58, 40, 7, negative 14, 14, negative 9, 18, 16, 79. First of all, let's multiply these two guys, right? The first two matrix there, I can multiply these guys, right? So this by that, okay, 0 by 0, there are 58, that's 0, 0, that's 18 here, right? And then 0, 0, that is 16 here, and that's 79 there, right? And then 0, that's negative 14 there, right? 0, that's 14 there, right? Okay, that's negative 9 there, okay? And then finally, that's 58 there. That is 40 there. That is 7 there, right? And then this guy multiplied by matrix 0, 0, 1, right? Multiplied by the product, the resultant of what we got. Okay, I've just used my Shan here. I don't know. If there's any mistake, guys, please let me know. $40 and then 7. Now let us multiply row by column. So this is 1 by 3 matrix. Okay, and then it's a 3 by 3 matrix. So K value be 1 by 3, right? Be 1 by 3 type, isn't it? So this row by the column 0, this 0 is 58, right? Okay, that's 40 there, right? And then that's 7 here if you multiply them. Okay, remember it's row by, so this multiplied by this plus this multiplied by this by this is first element right here. This by that, second element right there. This by that, third element right there. So those are the values of K, right? So meaning K1 is equal to 58 according to this, or K2 is equal to 40, K3 is equal to 7. I don't know if there's any mistake or something like that. Okay. So I don't know. Okay, so that's the final answer. You guys can confirm if everything's okay there. Okay, 58, 40, and 7. Okay, so I think I'm going to cut this video here. The next part, I'm going to upload it later. Okay, so I think this video is too long, so I'm going to cut it here. Oh, about 1 hour, 42 minutes. No, too much. You guys are not going to finish watching it, bye-bye. So I'm going to end it. I'm going to upload another video, a marathon again, different questions, okay? So that's the end, guys. Have a good day. See you next time.